Hi everyone, Adam here from the Jacobs Institute, and this video will introduce you to a template that we've designed in order to apply CAM pathways to solid models that you've created, maybe in other software. CAM as a field, computer-aided manufacturing, is infinitely deep and complex and can take many, many years to learn and master. And so we're hoping that this template will give you a little bit of that introductory experience you need to get started. So without further ado, let's get right into it. So I'm going to open up E29 Spring 2022. When I open it with an educational license, it should populate this arbitrary part here within this arbitrary stock. So it should open up into the manufacturing workspace because that's how we saved it originally. But I encourage you to go into the design workspace to just check out what all is here. Without getting too deep into the CAD, right here we have a representative stock model. And what we've done with a stock model is we've changed the opacity control so that it's 50% opaque as opposed to 100% opaque. And that's just so that we can see our model within it. And this is just so that when you import your model, you can use it as a baseline for where to place it. So the stock is 8 inches by 8 inches by 0.71 inches, which is the approximate thickness of our nominally 3/4 inch ply. We've created this arbitrary part so that it utilizes a number of different CAM pathways. This could not all be done with the same operation. There's a topography here that is going to take some figuring out, as all CAM pathways do. So we also have, so this is our part. If we wanted to make any edits to it, you can go into our sketch here and make changes to the sketch. Let's make the stock unselectable for a second. If I go in here, and let's make our part grounded for a second. I can go in here, and if I change any of these sketches, it's going to update accordingly. I just did a Control-Z undo, but you get the idea. So if I drop into the manufacturing workspace here, you can see that we've created a setup, and this is something you would do on your own. If you were going to do this from scratch, you'd start by making a setup. And then in this setup creation window, we have a number of options, things like creating our stock box origin, choosing our model. In here, for our stock, we can choose, and let me minimize this. And if we choose the model here, we can make our stock a fixed box size, which is if I happen to have a blank that's 8 inches by 8 inches by 1 inch or by 2 inches, so on and so forth. I would create it here, or say I had a full sheet of plywood and I just wanted to place this somewhere on the plywood and cut it out. I can use relative box size where I just, I have my X and Y, Z coordinate somewhere on it, and then I reference just somewhere on my full sheet of stock. So this has all been done for you. I'm just pointing it out in case you wanted to try it on your own. A setup was created. We've chosen your X, Y, and Z plane. Here we have our X, our Y, and our Z. And what we've done is we've created our Z origin point on the top surface of our material in the corner that we're expecting to be closest to the Shopbot computer, which is just by convention. And then our X and our Y hug our material. On the Shopbot, the X is the longest axis and the Y is the shorter axis and the Z is the vertical axis. So that's the box point that we've selected there. And then our axes are selected here. And then for the fixed box size, we've chosen the max amount of space that we're allocating for this part, which is 8 inches by 8 inches by 0.71 inches. Nothing else really needs to be changed here. These will serve as our defaults. So in here, we have quite a few operations. In truth, many parts can be done in a single 2D contour cutout operation, or your part might only need a single boring operation and then a 2D contour to cut it out. Or maybe you only need an adaptive or a pocketing operation. You should do some experimentation to see, what the most efficient or practical toolpath is for your particular part, which is going to have its own features. But in general, when you're machining, you're going to work from removing the most material as quickly as possible to finer detail cutting with, say, a ball nose end mill or smaller end mills. Now, for our purposes, we're going to try and use all the same end mill. And the rationale here is that we're cutting a lot of parts. We're trying to do it in a very short window. And so not having tool changes makes it possible for us to process all of these files. And so all of these paths use a 1/4 inch down cut flat end mill. And all of the speeds and feeds have already been dialed in for you. So let's just right click where it says face, choose edit, and just take a look real quick. So right now we've chosen a spindle speed and a cutting feed rate that is going to result in this feed per tooth, which is particular to plywood and works pretty well for us. Technically speaking, we could change these a little bit. We could increase the RPM and then increase the surface speed accordingly. And as long as we're hovering between, say, 0.03 and 0.04, a little above, we should be good for our feed per tooth for plywood. It's pretty flexible. So don't change any of these speeds and feeds. In stock contours for our facing operation, the facing operation is generally to take your material down to whatever ultimate height you want it to be shaved down to. So we've deliberately designed this part so that you need to do a little bit of shaving. Now, if you design your part to be 0.71 inches thick, then we can skip this step. So all it does is it takes it down to the proper dimension for a face. Normally you would face with a 2.5 inch fly cutter or some bit to really take the whole face of the piece down to one uniform height. And so it's parallel with the spoil board. And then we've set our maximum depth of cut here to 0.1 inch, which is less than you can do with this bit, but just for a facing operation, that sort of makes sense here. For the adaptive clearing operation, Fusion 360 has a really excellent proprietary adaptive clearing algorithm that's very good at finding an optimal way to remove the most material possible with a particular bit with your particular settings. And so very often, one of the first operations you do on your part is going to be an adaptive clearing pass, or in 3D, a pocket clearing pass if, say, you're making a bowl-shaped object and you're trying to remove the inside of that cavity. There are a lot of options in here. So we have our normal speeds and feeds. We've selected a geometry just around our part. And then actually, we can even select the second internal geometry. This is not in the template, but you can do this if you want to experiment with making some changes. And then in clearance height, that'll determine the maximum top and the bottom surfaces to which we want to machine. So instead of machining down to the stock bottom, we could do the stock bottom with a 0.05 inch offset, things like that. It'll make it so that we're effectively tabbing our whole part into stock that we're not cutting through, but we're not going to do that. And then in passes, a couple important things in passes. Number one is stock to leave. If we want to leave like a very thin skin of material around our part so that we can take it off later in a finishing pass, this is where we would choose to leave that very thin offset of material, both radially and axially. So on any kind of surfaces parallel with the spoil board or any surfaces that are not parallel with the spoil board, that can be decided here. Another very important variable is the maximum roughing step down. If we don't have a maximum roughing step down selected, the bit will try to machine the entire depth of cut for our part, no matter how deep it is. So it's very important to have one of these set. This is set at 70% of the bit diameter. In truth, with plywood, you can go a little bit more than that. I've even seen 1 diameter or 1.5 diameters, depending on your step over. But this is a good, nice and conservative baseline. Other things we might want to consider, if our part has any kind of like dish-like surfaces that descend in a very shallow gradient, we may need to machine shallow areas engaged so that it'll kind of machine at very small intervals across that gradient. And then in linking, our ramp into our material, we've set to a helix. So rather than plunging straight into our material, which may even be fine for plywood, we're going to ramp down into it and then do our cutting operation. So let's leave all of this as is. A couple more here. We have a ramp toolpath, which is going to just gradually carve its way into our material. It's good for getting kind of even contours, especially when you're using a ball nose end mill with a flat end mill. We'll still be able to get some of this done, and then you could conceivably go back in by hand or with a random orbital sander and smooth this out a little bit. If you want, you could even take the ramp at a shallower angle. Let's say if we go into maximum step down and we change it to 0.02, you'll see that now these steps are in a finer detail. And so the trade-off here is that your toolpath will take longer to execute, but you'll get a higher resolution of this curve. Following that, we have a boring operation. Boring is great for creating precise inside diameters in circular holes. So we've done a boring operation that is going to bore out this top circle and then bore out this bottom circle all the way through. Then we have a drilling operation. Now, drilling, you don't really want to do with an end mill. You really want to do it with a drill bit, which is more designed for removing material during drilling operations. Now, especially since we're planning on using a down cutting end mill, which means that as it cuts, it's going to be forcing the chips straight down, which creates burning and kind of wears on the bit. So if you're going to do a drilling operation with the same bit that you've used for prior operations, which just happens to be one of the constraints of this process, you want to do a full retract. Don't go down into the material too much, then do a full retract. And you can see here that what we've selected is deep drilling, full retract. And so it's going to peck down a certain amount, then retract, peck down, retract. And this prevents burning and helps with chip evacuation, especially when we're using a bit that's not really meant for this. The other thing you can do is you can drill, just instead of drilling the whole way down through this hole, you can use your heights tab to drill to the whole top with a very small offset. And what this means is that it'll drill a little way into each of your holes, and then you can go back later with a drill press, and that hole will help automatically align any drilling operations you do, so you can do them manually by hand. We'll leave it as is because this is a pretty shallow drill anyway, so that'll be fine for us. Then we have a slot operation where it's basically a ramp. It'll ramp down into your material to create a slot. And then we have a 2D contour cutout, which is very commonly the last operation that you'll use on a piece like this. And so we've been very conservative with our tabs. We have a lot of tabs. It's better to have more tabs and then have more post-processing than to have too few tabs and then you have parts of your assembly just being pulled off, ripped out, and then being sucked up into the ventilation, which is a big headache and actually can risk both your part and the bit and the machine. So we've created a bunch of tabs. The way the tabs are created and removed is in the geometry tab of 2D contour. If you look under tabs, we have our tab width set at 1/4 inch, and then our tab depth at 0.0625 inches. This is a very shallow tab. And so that's one of the other reasons we have a bunch of them. Probably better here, you could get away with fewer tabs if you go up to 0.1 inch tabs. So this is maybe a recommendation here. You could do slightly fewer tabs at 0.1 inch and you won't risk your part coming out during manufacturing. So I'm actually going to leave this here. And then let's go into passes and just make sure everything else is fine. Actually, there's one other thing that we need to tick here, and maybe actually I'll replace the template. We need multiple depths. And so in multiple depths, actually, let's leave it ticked off and I'll show you in the simulation what's happening here. So if we simulate the whole thing, which is something I recommend every time you do a CAM operation, it's constant simulation. I'm gonna hit simulate, and I like to have stock ticked on and toolpath ticked off. And that's just because this can butter things up. And I like to have a good vision over what's actually happening. So we have our facing operation first. Then we have our adaptive clearing operation, which is going to go down in layers, getting rid of the most amount of material. And then we have stop on collision selected. And this is going to tell us whenever we're going to exceed the parameters of our tool. And sometimes if it's just very briefly, like you can see here, that it wasn't expecting this collision with this tiny corner, but in practice, this is going to be on, and this won't stop the machine from operating. And in fact, it won't endanger the bit. And so we can just, we can skip that one. We can allow that one to exist. Descending into our material, and let's see what this is. Looks like we're colliding with the edge just a little there, which should also be fine. It'll just shave off the edge a little bit. All right, ramping down into our core there. Now, if you had left the adaptive pass the way it was and didn't put that extra geometric curve on the inside, then the adaptive clearing pass would carve out that entire cavity in the middle there. And the benefit of that would be that you wouldn't have to worry about this plug coming loose at any point. The downside is, of course, that it would add a lot of time, adds machining time, adds wear on the tool, that sort of thing. So now in here, oh, we're still doing our ramping operation around that spline. Oh, here's our boring operation. Oh, it's good. And then we have our pecking drilling operation. That seems fine too. And then we have our slot, which could maybe start a little lower, but that's okay. And now we have our 2D contour cutout operation. And if you don't see the issue here, then zoom in a little closer. So what we're doing is we're taking the full depth of cut, which could be up to and including the full depth of the stock with this pass. Now, it's not identifying it as a collision because it's kind of what we told it to do, but we really can't do this. We can't take the full depth of the stock with this 1/4 inch bit. So what we're going to do is we're going to right click 2D contour, and we're going to go into passes, multiple depths. And if you get a template that already has this done, it means that we replaced the template, but otherwise you'll have to do this. So the maximum roughing step down, we're going to set that to 70% of our bit, which we'll do just 0.185, I think it was, 0.895, something like that. This will be close enough. And so now if I hit OK, and then this safe distance warning, this will happen. But it'll retract this automatically. So I'm going to ignore this warning. You'll see now, instead of doing this all in one pass, it's going to do this in 4 passes. So go on to simulate, and then let's go to the next operation, next operation, next operation. Okay, so now you can see we're doing this in a couple of consecutive cutout operations. This will be safer, and then on the final pass, you'll see that we've left these tabs, including on our inside here. It's easy to forget this negative space, but you have to tab. Anytime a plug is going to come out or a piece is going to come loose, you have to make sure to tab it. Okay, so that's kind of a shallow pass over all of these different toolpaths that are possible. Let's say you've designed your part and you want to use some of the speeds and feeds and toolpaths as they exist here. How could you do that with this template? Well, I can go into design, and I've prepared on the back end here, if I minimize, you can see I've prepared this arbitrary file.step. So say you design something in SolidWorks, it's to the right dimensions and you want to bring it in to Fusion 360. So what we're going to do here is we're going to do open, and we're going to do open for my computer. And I'm going to open the arbitrary file.step. It has a lot of the same kinds of features. So I brought it in here as a step file, and then I'm going to save it, and I'm going to save it as arbitrary file, v1. And then when I'm in this file here, which I actually need to save to, and then you'll save this as group number, so group 34, Adam. I think we had an underscore here between group 34. I'm going to save it. So if I go into my designs and I show the designs within this folder, I see my arbitrary file v1. I'm going to right click that and I'm going to insert it into the current design. So that should just drop it into the middle here. And actually it's placed pretty well. So I'm also going to go into part 1 and I'm going to minimize my part 1. So if you have to adjust the height or anything like that, you really want the base to be on the bed. And so it depends on how you designed it. I might come in, at a right angle. And so you want to move it, and you may need to set your pivot point to the bottom, confirm, and then we can move it by moving it up, snap it to the bottom of our stock there. Okay, so once we have it positioned as we like it, I'm going to hit OK. And now we can go into our manufacturing workspace, and in my setup, I can edit it, and I can re-choose the, so instead of that original body, I'm going to X that out, and I'm going to choose this new body. I'm going to hit OK. Now we get to just step through and see which of these we need. So do we need a facing operation? Well, this new design does have some space above it. So I'm going to leave in the facing operation. I'm going to right click, edit, and I'm going to find in my geometry tab this chain, which is now outdated. It's the old object. And I'm going to replace it with the outer contour of this new object. And I shouldn't need to change anything else here, which is the beauty of this kind of parametric design, where we can update things in the past and have them propagate to things in the present. So now you can see it's changed the toolpath so it works on this object here. For the adaptive clearing path, I'm going to do the same. I'm going to go into geometry, and I'm going to select the outer geometry here. And I'm just going to leave the inner geometry like this. So just that outer geometry selected. I hit OK. And now it's going to regenerate the adaptive clearing pass so that it kind of deals with all of those internals there. For the ramp operation, it looks like we might still benefit from doing these curves, and maybe even these curves as ramp operations. So I'm going to hit OK. Cool, that looks good. Now this is a chamfer and this is a fillet, so I would have to then go back and sand them or file them. And then for our boring operation, it looks like we do have a boring operation in the middle here. So I'm going into geometry, deselecting circular faces, and let's just bore that out right there. For drills, I do also have drills. Now you're not going to need all of these. Your part probably will not need all of these. And so if there's one that you don't need, let's actually say, because it actually doesn't need a slot. So there's no slot on this. So instead of using this, I'm just going to go in and do suppress. So now it won't affect anything. You could even just hit delete if you know that you're not going to use it, but suppressing it does just as well. And finally, for the 2D contour, we not only need to change the geometry of the inside and outside, but all of our tabs are going to be wrong. So instead of these 15 tabs, I'm going to X this out. I'm going to select tabs for this model. Now, I recommend, sometimes if you have a spline curve, it won't let you select them, which is kind of a bug in Fusion 360. You may need to choose, instead of at points, you could do by distance. But if you're going to do, I find I have more control with at points. I can kind of like decide where they go a little better. Now you want your tabs on outer surfaces because they're a little easier to sand off, say on a belt sander or with a random orbital sander. If you put a tab right in the middle here, it's going to be a little less easy to process. And so sometimes you have to, but if you can get away with not putting them on inside curves, that's sometimes to your advantage. And then inside here, now these two pieces are going to come loose unless they're fully adaptive machined out. Now, I think we actually did machine them out. So let's take a look here. Now, pretty close. So I don't think we need tabs there. We should note also, though, that there are a number of features that are impossible on this model. So for example, this inside corner here, the bit is not going to be able to get fully into that unless the bit were infinitely thin in diameter. And so I'm going to have some radius corners also in here. And I may need to process those after the fact with a chisel or a file or something like that, or just redesign my part so it either has dog bones or Mickey Mouse ears, they're sometimes called, or these inside corners are themselves radiused. But I'm okay with them just being radiused from the manufacturing or from the machining process. So I'm going to leave them as is. So now, if we simulate it, hit play, got our facing operation, got our adaptive clearing operation. Got our ramp operation, boring, drilling, and then 2D contour cutout with tabs. So pretty good. Actually, very little work in CAM in order to transfer those toolpaths that exist in our template to our current model. Now, it's also true that I designed both models, and so it's possible that yours won't conform exactly, and you may need to experiment with a scallop operation or a spiral operation, or maybe any number of things can happen. You know, you may, if you're doing like a topographic map on top of your product, then you may need some parallel passes. So there's lots to consider here. You should do a lot of experimentation, but as a baseline, we're hoping that this template helps you in your processing endeavors. So please let me know if you have any questions. adamhutz@berkeley.edu, and best of luck. I'm looking forward to seeing your files as they come in.